Very good morning. Welcome back to the analog electronics course. So I'm expecting today, I think in our syllabus, if you see step 7 we are entering. Till now we have completed up to step 6. I have written like a stepwise in the syllabus. In the first page you can see nearly 12 steps are there. So today onwards, the countdown will start. Daily one step I'll complete for you. That is the target. By Friday, I think for ECE, analog electronics will be completed. This is my target. Today, I think the step 7 we are entering, called as morning session will deal about multi-stage amplifiers, which is our module. In the afternoon session, I have planned for differential amplifiers. These two modules are sub-modules to enter into the subject called op-amps, operational amplifiers. So tomorrow onwards you'll see the real op-amp design part. Today, the backup knowledge we are covering in the subject. So in workbook also there is a separate chapter to practice multi-stage amplifiers. So today 8:30, by 1 o'clock maximum we'll finish this module. So we'll take a break. So 2 o'clock onwards we'll start working on afternoon session about the differential amplifiers. Afternoon. It also takes some 3 hours class. So morning class by 1 o'clock if you can complete multi-stage basics. Afternoon we'll complete the differential amplifiers. So tomorrow we can start applications. Tomorrow basics and applications of op-amps. So one by one we can start it. So very good morning to all of you. Very good morning. Swati, don't worry, networks lecture may be uploaded today morning, okay? Because the class happened at night, so today they'll upload you. Morning session, maybe by afternoon you'll get that networks video, okay? Because night has been completed, so they'll go to home. So that is the reason morning they'll try to upload for networks. Analog, I think it is being uploaded in the in your PDF file. What I can say, in your course it has been uploaded. I'm expecting in your app. So today we'll start our main course, multi-stage amplifiers. After covering these fundamentals, multi-stage basics, we'll try to the workbook practice a separate video, okay? First we'll understand the simple basics of multi-stages, which are very important to understand the design of operational amplifiers. Okay, they're not very tough, easy to understand, easy to capture the concepts. No problem, Panja. If you're absent also for previous class, no problem. You can listen this class as a separate class, no problem. You'll not get any problem. This is a separate lecture. Ujjwal Kumar is telling today is my first live lecture of analog. It is your first live. We are in the climax of analog electronics. Okay. So how much you can understand, you understand. Otherwise, you can go back to my lectures, recording lectures, and you can study one step by step in order. Okay. This is my, I think nearly I completed around 40 lectures. Okay. Now you are coming. So my sincere advice: read the previous lectures and develop this concept. Otherwise, you can't understand some languages what I teach in the classes today. That is my sincere advice, Kumar. So let us start the syllabus topics what we have to cover today. So keep the heading topics in multi-stage. Write on the topics. Write on the topics. So the first topic we are going to see types of basic amplifiers. Types of basic amplifiers. Very important concept. Types of basic amplifiers based on Zi and Z0. Based on input impedance and output impedance. How can you make classification of amplifiers? This topic is very important. Maybe in GATE exam so many times you ask these fundamentals. So today I'll understand in brief what is these amplifiers. Second point, effect of cascading on voltage gain. One important concept. How voltage gain will affect in cascading systems is my second point. They're very easy here, okay? Don't get tension on these topics. Very fundamental topics there. Each and every topic will go into your mind today, no worries. Second topic is we're understanding how a multi-stage system will affect your gain, voltage gain of your system. Yeah, Ashish, okay, I've seen your message. Definitely 1 to 2 in between we'll take a break, no worries, okay? 1 to 2 I'll complete the course. Around 1 o'clock we'll complete this course, multi-stages. Then we'll take a break around 1 to 2, don't worry, okay? We'll take around 1 to 2 only break. Second, next point is effect of cascading. Effect of cascading on bandwidth. Effect of cascading on bandwidth. These are the very interesting parameters when you're designing a multi-stage systems. Today we are going to understand the gain effect using multi-stage electronics and the bandwidth effect, how the formulas will be, how to apply for the questions. These are the two important parameters. Anybody want to design a multi-stage system, first you try to understand the two terms. One is a bandwidth and one more, we have is a voltage gain. Not only these two things, one more interesting point we have to learn in multi-stage is the speed of operation. A single stage generally will have high speed. If you go for multi-stage systems, then automatically the speed will decrease. How to measure that speed of a device, of a system is, we have one more parameter for that to measure. Effect of cascading. Effect of cascading on rise time is very important, which is called TR. Rise time always specifies the speed of the operation of the system. How much speed your system is responding to your input will be measured by rise time. So before designing an operational amplifier, the scientists started doing research on a multi-stage system on 3 parameters. One is voltage gain, one is a bandwidth, and one is a rise time. Today class we are going to understand the conclusions based on these 3 topics. So these are very simple understanding points. First topic is a major topic today to understand how many variety of amplifiers we can do. This completes the concept behind multi-stages. But today we are going to learn some specializes designed in multi-stage systems. Most probably we use in number of bits in analog electronics. What is that specializes? We are learning as 5th and 6th topic. 5th topic is cascode IC amplifier. We are going to study some IC amplifiers. One of the popular amplifier in analog electronics. Cascode ICs we call this as. A cascode, whenever you use the word cascode. So Arpita, very good morning. How about your health here? I think you got fever you said. No, alright. Arpita, are you alright now? You got fever you said for 2 days before I remembered. So now if you're, I think from today onwards I think you're not attending the class because of high fever. Now if it is good, please reply. If you're good enough. So cascode IC amplifier we have. Okay? Cascode IC amplifier. A cascode IC amplifier is a cascading of a common emitter with a common base. So whenever you cascade these two transistors as an amplifier, common emitter to common base, whenever you do cascading this one, then it will become a cascode. In general, anything you connect two transistors we call cascade. But there's a special word for this application called cascodes we say. In exam, they'll say, okay, Arpita, great. So today class onwards we are entering to op-amps. For that today foundation we are developing called multi-stages. Try to start smoothly and understand the subject. Okay, 5 days I'll work for op-amps for you. So cascode IC amplifier is a a separate IC without analog electronics. It is widely used in cascode systems in your TV receivers. At the receiver side of your TV, we require high gain and high bandwidth. At a time, if you want high bandwidth, bandwidth is meant for to receive the signals, and at the same time, high gain is also required. Then at the time, the special amplifier we are using. The specialty of cascode system is high gain with high bandwidth at a time. But in normal transistor amplifiers, if you have high gain, we are not getting high bandwidth. If you have high bandwidth, we will not get high gain because gain and bandwidth are inversely proportional to each other. But this is a special one. Yeah, fine, everything is good, nice. So the next, this is one of the important design today. This is a very important design. And sixth one, Darlington pair. Darlington pair. Darlington pair IC. This is also an important IC vehicle, which is widely used in multi-stage electronics. So this is called a connection between two common collectors. Whenever you connect between two common collectors, we call it as Darlington pair. Okay, two common collectors when you connect, we call it as Darlington pair. Darlington is a scientist. Around 19th century only, he investigated one thing is, this system will give very, very high input impedance. Yesterday somewhere I taught you, whenever an amplifier have high input impedance, it will solve loading effect. So common collector, whatever impedance you got, if you connect two common collectors, it will give more than that input impedance. How much impedance will increase more and more, loading effect will dissolve that much. That's why in IC designs, Darlington pairs are the most important pair we use to solve this loading effect problems in electronics. So maybe this is for loading effect, this is meant for high gain and high bandwidth techniques. This will give high input impedance. This is the specialty. High input impedance. Darlington pairs always give high input impedance. And this will give the specialty high gain, high voltage gain with high bandwidth. At a time both things, this special IC will give. So you can highlight these things, when we study it, we'll understand. Cascode ICs will give high voltage gain with high bandwidth. Okay? At a time we'll get both the things. That's the beautiness. Darlington pair will give very, very high input impedance to solve the loading effect. So this is our today course actually. The 6 topics are very interesting to learn today to understand your op-amp designs in the next class. Only 6 topics, it's not a big module. Hardly takes some 3 hours to continue this subject. 3 hours ke baad, we'll do 1 hour practice on workbook. By 1 o'clock we'll reach the content. Okay? 2 o'clock smoothly we'll start the input stage of op-amp called differential amplifier study. Is afternoon class for about 3 hours continuously we'll cover. Okay? If it is crossing 4:30, 5 also, we'll complete by 5. Maybe then networks will take at 5:30. Okay? Because the timing is under control, we can control this. Okay? The module has to complete today. That is the target. Because I got the schedule now, I have to go to Jaipur now. By Sunday, Saturday they called me, but I said up to Saturday my schedule will not complete. I said so Sunday they have planned me class in Jaipur. I said by Saturday we have to reach the subject. But Friday EC students will be completing. So Saturday morning to evening we'll complete some device part of PN junction theory and some basics of BJT will be covered on that day so that electrical students also will be completed total action. Okay? So by Saturday we'll close the story of total branches. 2 branches will be completed. So this is about your multi-stage amplifiers, 6 topics. So let us start one by one. Smoothly we'll understand the fundamentals. After that we'll apply this knowledge in the work. Then we'll get a practice. Okay? Maximum 3 hours we can complete it. So now the time is going around 8:45. Now the time will start. So take them. So there are 6 topics. The first one we are talking about types of basic amplifiers based on input impedance and output impedance is the first lecture. The second topic will be effect of cascading on voltage gain analysis. Next topic will be effect of cascading on bandwidth. Next is effect of cascading on price time. These are called characteristics to understand how a multi-stage system will work. Lastly, we have 2 different ICs which are very popular ICs in analog electronics. Yes, Arka Mundal, electrical gate syllabus will be completed by Friday only. Saturday is an extra syllabus I am teaching for ESC. Okay, gate syllabus will be completed by Friday. EC and electrical. Okay, that extra day I am teaching not for gate. ESC syllabus teach karna. That is called PN junction theory. Some theory part is there that I am covering in the last topic called as Saturday class. So by gate, if you are preparing, so I think Friday will be the last for gate. Okay, Saturday is an extra syllabus for ESC students. I think Ujjwal Kumar, Patna Center, I am expecting will be open first. Okay, Patna will be open. October 15th I am expecting to be open. Patna and Lucknow maybe I am expecting first they will get open. After that Kolkata centers and Bhubaneswar. So actually the device part at that time I said 2 days, but what happened in our class is MOSFET I already completed my device part. Previously I covered it, so some part is gone. And in BJT I covered the early effect and basic modulation technique. वो भी cover हो गया, so very less modulation remaining. Only PN junction theory and some basics of BJT remaining. Already some device part I covered in BJT and MOSFET. That's why we don't want to touch BJTs and MOSFET. We want to touch PN junction theory in the final class. Okay? Indirectly I covered it already in the device part. That's why 2 days are not required. 1 day is enough for completion of the ESC syllabus. If you have ESC के लिए PN junction theory I'll teach. There's an extra topic for you. That means how a PN junction theory is formed. What are the principles behind that? That is the last class for you. Okay? Other than that, BJT is completed device part. Already you have seen early effect based with modulation. That is the device part actual. And some more extra BJT device part is there that I'll explain after the completion of PN junction theory. So 1 day is enough for that. Okay? Morning to evening it will complete. Don't worry. So when I don't ask me all these questions, time waste हो रहा है इधर. Okay? वो networks का बोल रहे हो क्या है वो देखते future में हो जाएगा ना. ये online का option भी होता है. So don't ask me all these questions at this moment. Time waste हो जाएगा subject का. Please take them. We'll start our class. Don't distract my mind to some other points. So try to start. Break will be there for this lecture. After 1 hour, around 10 o'clock, we'll stop some points and we'll make it as a second video. Okay? Breakfast के लिए आपको break चाहिए ना? Today we'll take less break. Hardly 20 minutes break I'll do. In the 20 minutes we'll make it a breakfast and we'll finish the next part like that. We'll make 2 parts this theory today. Okay. Rajneesh Kumar छोड़ दीजिए offline हो सकते देखते हैं क्या क्या होते. So let us start with the first topic. First topic. Types of basic amplifiers. Types of basic amplifiers. Please note down parallel with me. Don't waste the time. Types of basic amplifiers. Okay? He's asking on what basics is based on input impedance and output impedance. So he created some amplifiers like this. This is type 1 I can say. Type 1 you can see how the E-plane model I'll write. Suppose you have the input impedance as ZI. This is ZI. Output side we have some source called voltage source you got as AV into VI. And we have some practical resistance for a voltage source is Z0. This is your one model I can do. This is VI, This is P naught. This is one model here. So type 2, if you see, type 2. Type 2 you can see. The amplifier model I'm writing, ZI. Next, current source, AI into II. Here current has to enter. Parallelly, we have Z naught. And this is your output. Here also you need current. This is another way of designing an amplifier, type 2. So let's see type 3 amplifier. Type 3. ZI. Next we have is current source, GM into VI. This is Z naught. This is your output. This current is I naught. This current is I naught. This voltage is VI. Input is VI. And type 4. This is ZI. This is RM into II. And we have some resistance Z naught to the output. So what is this style of designing this amplifiers in the board? Try to understand it. So what is the styles here is? I just mark these points, you can see. One person is expecting VI has to go inside. One person is expecting current has to enter at the input. One person is expecting voltage has to enter. One person is expecting current has to enter. So we have input side, two parameters in the board, VI and II. If you are sending the current, voltage should not go into the amplifier. If you are sending the voltage, current should not go into the amplifier. That is our logic today. Okay? Okay, this is the story. So input parameters are VI and II here. And output parameters also, if you can see, voltage V naught can come out or I naught can come out of this amplifier. Voltage or current can come out. Here current is coming out, here voltage is coming out. So this is our story today. Different positions I'm creating your outputs. Sometimes V naught, if you want, I have to create V naught. Sometimes if you want I naught current to be delivered, you have to create I naught. So finally, there are 4 parameters in the board. One is VI, II as input parameters, V naught, I naught. So based on these 4 parameters, we have 4 diagrams in the models. Whenever there is a voltage source is coming, I'm writing in series the resistance. Whenever you are getting a current source, I'm writing it as parallel. These are basic networks. Whenever you have a voltage source is coming, I'm creating like a resistance in series Z naught. Whenever it is coming as a current source, I'm writing as parallel. Input impedance I'm defining by ZI for an amplifier. So from all these 4 types, now you have to discuss which amplifier, how to get these parameters. What are the rules we have to apply for input and output in ideal cases. Try to see now how to do this analysis. Suppose you are interested to go only the input has to go into the amplifier and this gain into input has to come as output here. So these 2 things should happen. So whatever you are delivering inside, current should not enter, voltage has to enter inside. Common sense use karo, voltage has to go, current should not go inside. Means current has to become 0 in the class. Current has to become 0 but voltage has to enter. So in this case, current has to become, II become 0 you want. When current want to become 0, what is the input impedance we have to take here is, naturally, it has to be infinite. So who will create an amplifier with a very high input impedance that will work like a, not a current control, it will work like a voltage control is telling. Means the total amplifier will be controlled by the voltage, not the current. That is the simple logic. So who wants? No one wants. In any device amplifier, voltage control if you want, the only simple secret is input impedance should become infinite. So current will become 0, but voltage will enter into the amplifier. So ZI should be infinite. This is one rule. That same rule here also you can apply. That same rule here also you can apply because you want your input, you want this current has to come out. So here also we are applying VI. But in this case, current has to enter. Current has to enter, voltage should not enter. Your current has to enter. So this is the consequences. So whenever they said voltage is entering, my answer will be very simple. I'll make the input impedance of the device or amplifier infinite at design. Always, whenever voltage has to enter into the action, current you don't want, then infinite impedance will create. So II will become here 0. Current will not enter. Okay. In this case, voltage should not enter. So VI has to become 0 here. Current has to enter, but voltage should not enter. That means if you make a short circuit, voltage will not enter. So it should be 0 is better. So 0 impedance is better here. And here also, voltage should not enter. Voltage should be 0. Therefore, it should be 0 is better. So this is the way how we got the knowledge, how to take the input impedances for a voltage control or a current control. So according to the board, this became a voltage control, this became a current control, CC means current control, VC means voltage control. Input part is completed, and this is a voltage control, and this is a current control. So like this you can finish some part of the name of your amplifier. The input part will be deciding your controlling nature. If anybody want to send a voltage into the amplifier, input impedance should be infinite you have to take. If you want to send the current want to be transferred 100%, but voltage should not go, then you have to make it as a short circuit. So ZI should be 0 is a current control. So this is a very simple thing. So logic is very easy. After completing this logic, the next logic is the voltage gain into input. If you make product, it will come as voltage V naught. That's why this product is called voltage. This voltage has to come here. This total voltage created inside the amplifier should come as output. Then automatically your Z naught has to become 0. If the voltage source, if you want to get as 100% V naught, the series resistance should be short. We have to make. So Z naught will make 0 in the first topic. It will become a voltage source. You can get as an output. This voltage source will come. So this will become voltage control. Voltage source will come out. With this property, we can bring voltage source. In this case, current source is created. EI into II. It's a current I naught has to deliver. If you want 100%, this has to deliver. This has to come out like this as a current source. Then the only secret here is, here we want to deliver the voltage. The only trick I'm saying here is, when current want to come out, your Z naught output impedance, we have to take it as infinite is better. For current source, infinite is better. For voltage source, impedance should be 0 is better. So here 0, here infinite. So we can get here, infinite means you can get a current source. So voltage control, voltage source, here current control, current source behavior is coming. Here, the same thing, current has to come out. Therefore, your output impedance should be infinite. If anybody say current source, no one words, infinite you can take. So voltage control, it will become current source. It becomes voltage control, current source will come out with this behavior. And here, output side, Z naught will make 0. Z naught impedance is 0. It will current control voltage source. Like this, we got four types of amplifiers. So one of the beautiful concepts in analog electronics, who can understand a simple manner like this? What has to come, what has to deliver out. Okay? Output modeling always for amplifier is very simple. When you have a voltage to deliver, series you have to keep Z0. If it is a current source, you have to take parallel. That is the thing. So what are these indications? AV means what? AI means what? GM means what? What is RM? These four things I'll explain in the next slide. First complete these points. Otherwise I'll give just the names if you want, I'll write here. AV means voltage gain. Voltage gain. AV means voltage gain. AI means current gain amplifier. This is a current gain. We can have four gains like this. GM means special gain called transconductance gain. GM means transconductance gain we call. And RM means transresistance gain. So in our life we don't have only two gains, we have four gains. So most of the times you see only these two gains, but we have four gains actually. GM is also a gain for us and RM is also a gain for us. Total four gains will be there in electronics. Maybe these two will not have units, but these two will have units. Yes, RM into VI will deliver to V0. RM into VI should deliver to V0. So I think here you have to show like this. RM into VI should deliver to V0. You have to show like this. So you can write these points. Very interesting topic. They'll come like one mark questions in analog electronics. So we should not forget these basic ideas. It's a very fundamental basics in electronics. So anybody want which type of amplifier, you have to decide the impedances according to that. I can tell you what type of amplifier it is creating. So it is entirely depending on the impedances of your device, amplifier device. So after seeing the board, you must get clarity today. When input impedance is infinite, we will say now onwards. Output impedance is 0 for an amplifier. We can call it as voltage control voltage source amplifier. If input impedance is 0, when output impedance is high, suppose that type of impedances you created, then it will behave like a current amplifier, which is called current control current source. And we will take infinite impedance at the input, output also infinite impedance. The device will work like a transconductance amplifier device. And the last device is input should be 0 impedance, output also 0 impedance. If the device works like an amplifier, we call the type of amplifier as current control voltage source amplifiers. So Rajneesh Kumar, AV means voltage gain here, AI means current gain, GM means transconductance gain, and RM means transresistance gain. I said one is transconductance gain and one is transresistance gain we call. So let us have some conclusion about these four topics. So don't forget there are four types like this. Everybody knows only voltage gain, current gain till now. We have not only voltage gain, current gain, we have transconductance gain is also there and transresistance gain is also there in electronics. Total four gains we can get a possibility with impedances. So we'll prepare some table form which is very beneficial for writing the objective questions in the GATE exams. Let us see the four table form analysis now with this concept. So please complete. Divyadas, one thing I want to tell you, your BJT, originally BJT device is falling under one category. It is behaving like one category, but analog electronics engineers can make four amplifiers based on BJT by using a concept called negative feedback in my last class. You must know some more knowledge. With the negative feedback, we can change the behavior of the amplifier. So I can make input impedance high, I can make output impedance low. I think yesterday you were saying in common collector amplifier. Common collector is giving high input impedance, low output impedance, means you have changed it. Generally BJT will give low impedance and high impedance. Correct? But we have changed it to high impedance to low impedance. That is due to RE, called negative feedback. These all things are called feedback techniques. So don't believe that BJT is always a current amplifier. It behaves like this BJT actually. This is the model we have seen in BJT classes. One is R pi, one is GM into V pi, and one is output impedance called R0. This is my model actually. But this model we can convert into four varieties according to the changing of the impedances. So a BJT can convert into four amplifiers. A MOSFET can become four amplifiers. So don't think that BJT will work only like a current amplifier. It can behave like a voltage amplifier also. It can behave like a transconductance, transresistance. That depends on your impedances. How you prepare the impedance in the design with the help of a negative feedback electronics. Okay, therefore, talented negative feedback system techniques. I can convert which type I want. This only in the last class we are going to learn called topology of designs. Without knowing the topology, analog will not look good for it. That's why the last class will be a very interesting class. The overall devices we are trying to learn at a time. BJT I can convert into four types like this. MOSFET I can convert four types. Op amps I can convert four types. Anything I can design it with the help of the concept called topologies. That will be seen in the final classes. Divyadas, BJT originally it is not voltage control current source. Common sense use karo. It's a current control current source. We just converted like a voltage control current source in RPI model. But originally it is a current control because input impedance is low. RPI is not a high impedance, it's a low impedance. That's why BJT comes under this category. But this conversion I made like this. I done like this and I studied called RPI model. So we can convert from one model to other model. Originally it is this one, which is called H parameter model. Style is this one. H parameter model I convert into RPI model like this. So because a BJT can convert one form to other form like this. Vishal, one thing please remember, the diamond shapes, all these things will come in network scores. In analog cores, all are dependent sources only. We don't have any independent sources to write like a diamond shape. Okay, if you want to write diamond shape, circle also you write, nobody will bother in exams. But in network scores, we have two different sources they'll give in the exam. One is dependent, one is independent. To understand the distinguish between independent and dependent, we try to take the diamond shape for the current sources and voltage sources. Is the tension here? All are dependent sources only. Whatever you like, you can do. Okay, anyway, if you complete these four things, let us start concluding our concept. Let us conclude it. So, type, you can write one side, table form you can write. It is easy to recollect in the future classes. One side you write type of amplifier, type of amplifier. One side you write type of amplifier, type of amplifier, and the gain. What is the gain for that? We have to take what gain for that amplifier, and what is the input impedance, and what is the output impedance. Just you practice like this. This will become an objective version for your competitive exams. The first one is voltage amplifier. We call this as. First amplifier name is voltage amplifier. Voltage amplifier can also be called as voltage control, voltage source we call. Voltage control, voltage source. The gain we are defining for this is AV, which is V0 divided by VI. It's called gain of this amplifier. Voltage gain is V0 by VI, is the voltage gain. And input impedance we have to take here infinite, high input impedance, here 0 low impedance. So who can prepare a device like this as an amplifier? If you can design like this, automatically this works like a voltage amplifier device. Maybe the best example in our class is infinite zero we got in common collector. So a common collector is behaving like a voltage control voltage source amplifier. That is the best example for you. In BJT class only I have seen. A common collector input impedance is high, output impedance is low we got. That's why it will behave like a voltage amplifier in electronics. It's a voltage control voltage source amplifier we got. It's a voltage control voltage source amplifier. The second one we have is current amplifier. Second one is current amplifier. Current amplifier is current control current source amplifier we got. Here current gain definition is it is a I naught by II. Current gain definition is output current by input current. It is also unitless. But here the input impedance we have to prepare 0, but output impedance we have to prepare infinite. So this is an opposite version of impedance knowledge about current gain to voltage gain. Voltage gain when it is infinite 0, current gain will be 0 infinite. It is an opposite reaction. Okay. And coming to the point number 3, transconductance amplifier. Transconductance amplifier, which is a voltage control current source. It's a voltage control current source, which is called GM. I'm giving the name, capital letter. It is output current divided by input voltage. Suppose you are getting confused with this name, sir, case voltage control current source. How you are written? Simple logic. Current source is output. I naught is output. That's a current source. Input is VI, so voltage. So voltage control current source. Seeing that ratio also you can tell. Dipyalas don't talk all these stories. Okay, they are active load only bata raha in any amplifier. If you can prepare input impedance high, output impedance low, it can behave that amplifier as a voltage control voltage source. वो बता रहा हूँ मैं. Active load लगाता हूँ sir, impedance increase करता हूँ वो नहीं बता रहा हूँ मैं. Unnecessarily don't divert that concept to some other places. Okay, here the basic meaning understand and leave the point. When to use that point we'll see in the further classes. So understand the basic meaning first. Unnecessarily don't react with the active loads all the stories. Active loads are meant for some other purpose here, not here. Transconductance amplifier is voltage control voltage source. The definition is output current by input voltage we call. Samresh, your chart is visible. Don't worry. Yes, you said a feedback topology. Yes, Samresh, correct. Feedback topology is one of the most important topic in analog electronics. Okay, that will come in feedback amplifiers called step 11 in my syllabus. So GM is I naught by VL. He said that if you want to make a transconductance device, both should be infinite is important. Both the impedances you have to prepare like this. What is the best example for transconductance device in analog electronics is your MOSFET. You already know the experience you got in MOSFET. We have high input impedance and output impedance is also high. So I think this is a MOSFET device example. But that MOSFET I can convert into other types. But in general, it behaves like this. But it can be reformed into different fashions by using topology network techniques. So basically, it works like this. BJT basically works like this. Okay, basically a BJT will work like this. This is a BJT example. Basically, it will work like this, and MOSFET will behave like this in general. But we can change it to 4 types if you want. In general, if they ask you how a BJT device will work, means current control current source it will behave. And MOSFET how it will work means it will behave like a transconductance device we call. And whatever the first case, infinite zero voltage amplifier, it is not more than op amps. In the next class, we'll see op amp devices. Like this in analog electronics, there are 3 basic amplifiers already created by some person. That amplifier, as a user, I convert into different fashions by changing the impedances at input and output. So we can play the game after designing the device. So basically, it behaves like a voltage amplifier. BJT behaves like a current amplifier. MOSFET will behave like a transconductance amplifier. What is the last one we have is transresistance amplifier. Transresistance amplifier. This is a current control voltage source. It's a current control voltage source. This is RM amplifier, which is V0 by IL. Output voltage by input current we call a transresistance amplifier. It is 0 at input. Output is also 0. In analog electronics, we don't have any basic device to tell the example of transresistance because no device in the class of analog I have seen 0 0 directly it is working as an amplifier. But we can convert whenever you want. Suppose transresistance behavior, we can go for topology designs and we can just convert the impedances into low and low and you can use it like an application whenever you want. But in general, this application most of the times we never use. Only these 3 cases will be running in analog electronics most of the times because 0 0 is not a good behavior for designing an amplifiers. Okay. So last case I cannot give any example for you. Only 3 devices in analog that has covered these 3 structures. So this is about my concept. So how to remember this technique actually? This order you can keep in mind. Infinite 0, we start like that. Infinite 0, 0 infinite, infinite infinite 0 0. That is the order. First to voltage gain, next to current gain, next to transconductance, next is transresistance. This completed my first topic of today class. Okay, this is not a very tough topic I'm expecting from the students. Okay, easy and comfortable ideas. So these are the 4 types of amplifiers which we generally use in analog electronics, using BJT devices, MOSFETs and op amps. So the first topic today is completed. So let us move to the next topics. By 10 o'clock, I think up to rice time I'll complete. After that, I'll give a break for you. Break apart, we'll complete 2 topics remaining. One is cascode systems and one is Darlington pair. Okay. The 2 topics will take as a separate video. Up to rice time we'll complete. So please memorize this techniques. Memorize these techniques. Throughout your classes, in exam point of view, they'll ask you these questions. For a transconductance amplifier, what will be the input impedance, what will be the output impedance, they'll ask you. Then simply say that infinite, infinite. Otherwise, practically high and high will be the impedances. Somebody asks a trans resistance, you have to tell that low, low. Otherwise, 0, 0. Voltage amplifier, infinite, 0, sir. Current amplifier, 0 impedance, infinite impedance. This is the story about my first lecture today. So here 2 gains will have units. These are the special units gain amplifiers. These 2 will not have any units. Voltage gain and current gain will not have any units. Only the units will come for GM and RM will have the units for the gains. So let us move to the next point. Concept number 2 we'll understand. Second topic. Topic number 2. Topic number 2. Second topic we're analyzing. Second topic. So keep the heading, second topic. Topic number 2 is, second concept, effect of cascading on voltage gain. Keep the heading, effect of cascading on voltage gain. I'll take 3 examples to teach this. See here. Suppose example 1 I have taken like this. Example 1. What is example 1 here is, suppose I have a gain of A1 is suppose a 10 we have, and second gain A2 has a gain of 10. This is called cascading. I have done 2 transistors in cascade. So this is my input and this is my output. Okay, you have given the input here Vi and we are taking the output here as V0. This is called cascading. So can I say that this cascading system is telling both gains are same, similarities. So that means in cascading system, taking the gains equal also no problem. Okay, you can take the gains at different also no problem. Like this we are seeing the cases now. Example 1 I can say. Otherwise type 1 you can write, it's better. Different ways how I use the gains. You take this as a type 1. The first case I'm seeing, type 1 case, is like this. So this concept we call it as identical gains we call. Identical gain concept. So identical gain. This is an identical gain we have given. Now suppose this input is giving some output here as suppose V0 dash suppose. Okay, V0 dash. Now suppose he is asking a overall gain now. That is AV is equal to V0 by Vi he is asking. That means a complete system gain he wants. He has taken 2 different gains, he is asking overall gain. From here to not here he is asking, from here to here he is asking. But what happened in cascading is, whatever the output came for the first system, that became the input of the next system. That means V0 dash is the output of the first stage, and V0 dash became the input of the next stage. That means if the output is not coming for the first stage, second stage will not work. So that is the concept of multi-stage. So why can't you divide this concept as V0 by V0 dash you can write. So from here to here is one gain into V0 dash by Vi. You can separate this gains into 2 parts. So V0 by V0 dash is nothing but A2 into V0 dash by Vi is nothing but A1. That means finally what is AVV is, the gain is nothing but a multiplication of the individual gains I got. So the 2 gains if you multiply, you will get the overall gain is telling in multi-stage. So these 2 gains if you multiply, what is the answer here is, your AV is coming to be 10 into 10. The answer will be 100. This is the gain we got for the multi-stages. So the gain is 100 we are getting. Okay. So finding the multi-stage gain is not impossible. Each transistor the individual gain first you have to calculate, and if you make it a multiplication, we'll get the overall gain. This is type 1 knowledge. So if I go for type 2 concept, type 2, sometimes the question will be like this. A1 I'm giving as suppose 5. A1 gain is 5. Then A2 gain I have given as a 10. 2 different gains I have given. This is your V0, this is your V0 dash, and this is your Vi. So this is another example you can see in the coming classes. 2 gains are different also we can see, which we can call it as non-identical gain concept. Non-identical gain concept it is. So one thing is very clear for me, it may be non-identical or identical, the gain formula is same. So the gain formula will be enjoying with AV1 into AV2. So it may be identical or it may be non-identical, the principle is same. Voltage gain of 1 should multiply with voltage gain of 2. So summary here, I'm not talking about impedance matching, nothing I'm talking here, I'm talking about cascading of gain concept. So don't divert your mind to some other things. Okay? Either हम क्या बात करें, please ask the question based on that only. Don't divert the minds. Okay? We're talking about voltage gain and concentrating the class. So AV1 into AV2. The answer will be 5 into 10. It will become 50. So can you see that he can make non-identical gains also? He can make identical gains also. There is one more type I can show you, special type now. Type 3 also can happen. What is type 3 here? You can see. Suppose my gain A1 is a 10. A1 is a 10. This is Vi. The next we have is V0 dash. The next what I have done is, here I kept some voltage buffer here. I kept a voltage buffer and I am taking the output. So first one have some gain 10, but the second one is not a amplifier, it's a voltage buffer amplifier I have taken. Everybody knows voltage buffer means the gain A2 will become 1 here. Buffers will give, gain will be close to 1. So the second case we have 1. Now what is the overall gain I asked you? You have said that AV1 into AV2. This is the gain again. But you have seen the logic, second one, AV2 has been disappeared in the class. AV2 has been disappeared in the concept. So I think here indications wise we'll write, sorry here, A1, A2 we can write here. I'm going here A1, this is A2. Notations will be confusing you. Sorry for that. This is A1, this is A2 will take, because in the box I have written A1, A2. So A1, A2 is coming as simply here. Can you see that only A1 is coming in this type 3 case? That means the single stage gain, whatever you have 10, the same thing is coming for multi-stage. So that concept also can happen when the buffers, if you connect in the circuits, because buffers will not have any gain, it will give only unity gain, such that the overall gain will become the first stage gain, because second stage is a buffer. So the answer will become here only 10. So you can see the story of last case. So these are the 3 variety of voltage gain effects can happen in electronics. So take these 3 concepts. With this we can conclude the statement now related to voltage gain. First topic, second topic is ready. This is about the second class. This class you'll enjoy because concepts are looking very comfortable to capture. So what is the statement here I can write? An important statement. So we can say a conclusion statement we can say. After studying these 3 examples, what is my good conclusion of this is? Conclusion we have to write. Type 1, type 2, type 3. After seeing that, what is the conclusion we can say? What is the conclusion is? The voltage gain AV of a multi-stage will be greater than or equal to voltage gain of individual stages. That is A1 or A2. So you can see this is the golden point you can understand in multi-stage electronics. After seeing these 3 good examples, I got this statement. Voltage gain of a multi-stage will be greater than or equal to the voltage gain of the individual stages. This is the concept I learned in the board. So correctly see the statement, you'll understand what happened. So it's telling always in electronics, who will take multi-stage electronics, that gain will be always dominating. It always dominates your individual gains. You can say 5, 10, but answer is 50 here. 50 is dominating A1 or A2. In the first case also same thing, 10, 10 you have given, but it is coming 100, 100 is more than individual gains. But last case if you say not only greater, sometimes it is equal also can happen. Only thing is buffer whenever you connect, a multi-stage gain and an individual gain will be same. So that can happen. So this is the situation, how we got the concept about voltage gain analysis. So this one property should be in your practice always. A multi-stage gain will be always greater than or equal to voltage gain of individual stages can happen. So next is bandwidth observation is my next concept. Concept number 3 we are entering, that is called bandwidth analysis. So please complete over here. Sitika, what is that zero? I can't understand what you have written. Sitika, what you are writing I am not understanding. So Sneha Kumari is asking in cascading, shall we take more than 2 stages? Means yes, you can take 10 stages also, no problem. Just have an example. If it is suppose 3 stages, we can write it as A1 into A2 into A3. Like that you can just multiply. How many stages you have, you can multiply it. Just for study purpose, I limited my concept to 2 stages. You can take any number of stages. Vishal, it is not parallel combination here, series combination wise will take. Okay, cascading will be in the form of series technique we are taking. So let us go for topic number 3. Another interesting observation is, topic number 3 is effect of cascading on bandwidth instead. There is one more interesting observation. Effect of cascading on bandwidth. Here what is the problem is, you can see the observation, your gain, voltage gain is always inversely proportional to 1 by bandwidth Z. From the gain bandwidth product what we studied in previous BJT classes, we got this knowledge. When bandwidth increases, gain will decrease. As the gain increases, bandwidth will decrease in analog electronics. It's a very common thing we have seen called FT knowledge. FT is equal to gain into bandwidth. Okay, FT is a constant for every device. If one side you have a constant, if gain if you increase, automatically bandwidth will decrease. So that is the story. Gain increases, bandwidth will decrease. Now the concept is, okay Sujita, okay, by mistake you have done, no problem. Because I can't understand that information, that's why I asked you, no worries. No worries. So let's say gain and bandwidth are inversely proportional. Now the point is, type 1 analysis I'm doing. Here we have 2 types again. Type 1. In type 1, what is the concept is, identical stages will see how the bandwidth will be. Identical stages. For identical stages, how the bandwidth you can expect. See, we have here, suppose, we have A1 is A. First block is having same gain, as the second block also have the same gain. Like this you are seeing. Both have the same gains. That's called identical stages. You have input here, you have output here. What you can say is, if you have the same gains, the bandwidth of the first stage, this is the first stage, and this is the second stage. The bandwidth of this stage, bandwidth of this amplifier, and the bandwidth of this amplifier will be same. Common sense is that. The bandwidth of the first stage will be equal to bandwidth of the second stage. What is the reason is? Because of identical gains. Because of identical gains. So this is the first concept a student should understand. Whenever you have 2 gains are equal, same gains, you'll have the same bandwidth. If suppose gain is different, then bandwidth will be different. So that is one logic you have to understand in this board. 2 stages you take, 10 stages you take, the overall bandwidth will be different compared to this single stages. These are all single stages. Now we have each bandwidth is same you are taking. Then overall bandwidth what happens? That is the concept. So you can see the frequency response for this. Suppose I consider this is your single stage bandwidth. This is your single stage bandwidth having some gain. This is the gain called A. For individual gain I have is A. And we have the 3 dB frequencies. One is FL and one is FH. And we have some 3 dB here, minus 3 decibels. Already we studied this concept. It will have minus 3 decibels will get the bandwidth. That means here A by root 2 we have to do to get the bandwidth. So this is called a single stage bandwidth, RC coupled amplifier bandwidth. Correct? Which we studied in voltage amplifier analysis. Lower frequencies will get attenuated by external capacitors and higher frequencies will be attenuated by internal capacitors. In our previous BJT class we have studied. Now the point is, for every stage you can see identically this way formula is coming. Because same bandwidth you have for first stage also, second stage also you have the same bandwidth. But he's asking overall bandwidth is how much. If overall if you do, I think automatically your bandwidth is decreasing like this. Because overall if you see, what is my overall gain here? If you observe, overall gain becomes A power n. A power n. A power n means here we have only 2 stages, so the overall gain will become here A square. A into A will be the overall gain. Compulsory overall gain is more than a single stage gain. So gain will come more for multi-stage. Now only I said as the gain comes more, automatically bandwidth has to decrease. So you can see as the gain is increasing more and more, the bandwidth is decreasing here. So here also you can see 3 dB frequencies. Here also you can see 3 dB frequency. So this is A square by root 2 times you have to take to get the bandwidth. Here also we have minus 3 decibels. Here also we have the minus 3 decibels. Here also we have minus 3 decibels. So like this we are getting the concept. Now what we'll do this frequency is F L of n will write. Here F H of n will write. In brackets, what is the meaning of the 10 is? How many stages you have taken? That n represents in the brackets. That is the overall n stages ka lower cutoff frequency, higher cutoff frequency. This is the story about my first identical stages concept. So one thing I understood from this board, whenever you take multi-stage systems, gain will automatically will increase. At the same time, there is a side effect for your system is bandwidth will decrease. So if you want to get one parameter you lose. Because bandwidth is also important for amplifier, gain is also important. But if gain increases, in electronics what happened is, these 2 parameters are reversely related in electronics. harmonics. That's why if you want one thing, other thing will be lost by you. These are the complications will come when you design the integrated circuits. So I'm expecting it's very clear. Typically they have derived the formula, which I don't want to give derivation for you. Standard formula practice karte. So formulas practice karo. We don't need derivations here. FLN of n is equal to, you have to have a practice on this formula, FL individual lower cutoff frequency divided by some factor you have to practice. That is root over 2 power 1 by n minus 1. This is one of the important formula to solve n stages ka lower cutoff frequency in identical systems. So these formulas generally, okay, I'm not taking much importance in my class because maximum exams में questions नहीं आते आपको, okay, bandwidth का problems will be coming very less. In GATE exams I think they never ask you. Maybe in ESE by chance they can ask you. That's why we're going to have a formula practice. FL by the formula is root over 2 power 1 by n minus 1. Just have that knowledge practice. That n refers to the stages. How many stages is telling? You throw that answer there, you'll get the n stages ka lower cutoff frequency. If you want fh of n stages ka higher cutoff frequency, it is fh into whatever the factor you got here, you just take it as multiplication for higher. So these are the two standard formulas which we can take the help to solve this type of questions. So FLN of n and FH of n and FH. We have two techniques now in the formulas. So let us have a good practice on these formulas. Whenever the question comes related to this, you can apply these formulas to complete the task. These are the very standard formulas in analog electronics. So we can have a practice directly. Okay. FL divided by root over 2 power 1 by n minus 1. It is not 2 power n here, be careful. It is 2 power 1 by n factors minus 1. And here 2 power 1 by n minus 1 under root. What is the specialty of 2 power 1 by n is whatever the quantity comes in the denominator, it will make FLN of n will come more than FL. The trick is opposite trick. If anything comes in denominator, we feel that it is decreasing. But because of the factor 1 by n, it will increase the value. That's the concept. So FLN of n should be more than we want. That's why denominator we have to keep that parameter. It will increase the value. If you multiply, it will decrease the value. If you multiply, it will decrease the value. It's opposite action. So here in the diagram, type 2 is also there. That also will complete the formulas based on this. I'm just magnifying it. You can see the complete view of these formulas. This is one observation in the class about bandwidth. So one more bandwidth we'll see and how to write the formulas for that. So in the exams they can ask you in ESE papers, in old papers I've seen some questions related to bandwidth. At the time the student requires only the formula, how to apply it and what case you are applying is important. So these are the cases. These formulas are very helpful for us when the systems they set identical stages. Okay? Because in our class we have two systems. Identical people सकते, non-identical also can happen. This for only identical systems. These formulas are valid. So nicely completed. Lastly, one more step is there. That's called non-identical stages. Yeah, Sneha Kumari, bandwidth ka definition. If you want overall bandwidth, the definition is that only. What you said is correct. I'll write the bandwidth definition here. You can see. Side by you can write the meaning of bandwidth definition here. So bandwidth, the overall bandwidth of cascade, if you want, bandwidth of cascade will be equal to fh of n minus fln of n. So this will give the bandwidth of cascade. Higher cutoff frequency minus lower cutoff frequency difference when you take will get the bandwidth. Higher cutoff frequency minus lower cutoff frequency is bandwidth. The meaning of bandwidth is where the gain remains constant. That region we call it as bandwidth region. The remaining part it is getting attenuated. That portion we are not including in the study purpose. Okay, because the gain is not stable in that region. Where the gain becomes constant or stable, that region we call it as bandwidth for an amplifier. So overall system bandwidth is coming less here compared to the first one. So we can write here in the second step we'll write and we'll conclude the concept. So can I expect it is completed? So Ujjwal Kumar here, what is the difference between FH and FL? Both subject might teach here, previous classes में. Maybe you are today only entered. FH means higher cutoff frequency both there. FL means lower cutoff frequency we call. Higher cutoff frequency will come in the higher frequency region. Lower cutoff frequency which looks like a band pass response for an amplifier. These are all things I covered in my BJT classes. That's why I'm sincerely advising you, start from the first video onwards. Otherwise this type of things will confuse your mind. Because we've done a lot of work actually till now. Very lot of work I have done it. And I came to the final stage called op-amps. Now the student who listens my classes, previous classes, is very comfortable to understand my lectures. Okay? Who is present now only that people can get confusions. Because he must have the background, whatever I thought. That's why my sincere advice. If you have any doubts, go back and study the total recording videos. So let us have one more picture. Type 2 we are doing, one more type is there. That is, type 2 is there. Type 2 is considered to non-identical stages. Type 2 is considered to be non-identical stages. For non-identical stages, I can take an example like this. This is A1 having gain of, suppose 10 is a gain. A1 is having a gain of 10. And A2 I have taken another gain of 20 I have taken. A1 is 10, A2 is 20. This is my input and this is my output. So what will be the consequence will come in the graph? So can I say the bandwidth here, BW1, the bandwidth here, BW2. Can I say that BW1 is not equal to BW2? Easily you can tell. Because you have two different gains, so bandwidth will not be equal. Two different gains will not have same bandwidth. Same bandwidth. This is the principle actually. If you have two different gains, you will have two different bandwidths in the graph. Let us visualize how it will be. Okay, Vijay Kumar, I think, okay. You said difference between FH and FL is the definition you said. But मेरे को कैसे लगा difference between FH and FL का meaning you are asking. Sorry for that. Okay, understood. Good, great. That means you are following the concept. Okay, that's great. I felt that previous subject is required for you to understand, but your understanding is a good thing. Nice. Good to see that one. Great. So two different gains will not have the same bandwidth because as the gain is more, bandwidth will be less. So here my observation is both gains are different, both bandwidths are different. Then how to show in the waveform? You can see this is your waveform. The first gain I'm showing like this. This is the first gain, which is called your A1. This is A1 and it is having some 3 dB. We have here FL1 will get and we'll get here FH1. This is the first gain bandwidth. First gain bandwidth is completed. Okay, first gain bandwidth is completed. The second one, you have said that one more gain we have where it is more than the first amplifier. So I think the bandwidth will change again. So this is your A2. Because A2 have 20, so the gain is more. So automatically the FL bandwidth also changes, FL2 and this is FH2. So this is the consequence comes when it is non-identical stages. So you get suppose the 10 stages you have non-identical, you have to draw 10 graphs like it. Each graph will not match to each other. That is the difference between the concept. Okay? I've done by all previous lectures. Okay, Ujjwal, great to see that message. Wonderful. If you've done all the previous lectures, you're ready to attack these concepts. Great. Nice. So A1, A2, we have different gains, we have different bandwidth. Now what is the overall bandwidth he's asking? Overall is nothing but what? Overall gain is nothing but, it's a cascading of A1 into A2. It's the overall gain. So overall gain will become 10 into 20. It becomes 200. I think this gain is very high compared to the individual gains. So I think your response may come like this. Maybe like this you can get. So this gain is your AV. Otherwise we'll write like this. In place of writing AV, we have some notation here called as A power n. N result we are finding. This you can write as A power n. So n stages we are finding the result. A power n. That n stages are nothing but 2 stages here. So A power n became A1 into A2. So you have the bandwidth again here. So this is your FL of power n. This is FH of power n. So here we should not write in brackets, we are write power because we want this result by n stages, we want multiplication wise. So previously we have only one FL, now we have FL1, FL2, FL3, all these things will come in the transfer functions. So that's why n result we want. So that is the reason here power n you have to write. Previously we have written in brackets, identical stages here, the representation will become power because of the n power result. So how to write these formulas? So first formula is FL power n. FL power n, what is the result here is, approximately if you want the answer, it is a square root function, FL1 square plus FL2 square plus so on, FLN square. This formula is very easy to recollect or remember. You have n number of lower cutoff frequencies. In the derivation we are getting it as a root over all the frequency squares, a square plus b square plus c square like that. So we have to find this resultant like this. This is FL of power n will be calculated in this manner. And this is not an accurate answer, it's an approximate answer he said. But suppose somebody want accurate answer, okay? Multiply by 1.01. So if you multiply by 1.01 times, it will become the accurate value because 10% approximation I have done, so 90% accuracy it is. So 0.01 if you add for that, you will get the more accuracy, which is close to 100%. When I'm doing this derivation, we have done some approximation that 10% quantities are left over and 90% approximation. So 10% if you want to reach, you just multiply by 1.01 he said. This is called an extra factor, okay? An extra factor for you to increase this value to the accurate analysis. Examiner, if they ask you approximate, you tell just root over f1. If they ask you accurate, you just multiply here some 1.01 extra before the square root. That is called accurate answer. Shabanidas here, we are just multiplying for n frequencies. FL1, FL2, FL3 like that you are taking. So how many stages you have, that much power n will come for this topic. Okay? That's why we say power n here. For the n stages we are multiplying for n frequencies. N result we have taken. This is 1, 2, 3, 4 like that. So power n is important here to represent. If it is FH power n resultant if you want for higher frequencies, it is approximately equal to reverse you have to take here. Root over, 1 by root over, whatever the frequencies will get, you write reverse answers. FH1 square plus 1 by FH2 square plus so on, 1 by FHN square. So this technique is exactly opposite technique. And the trans functions are reverse here actually. This is a high pass trans function, this is a low pass trans function, where we go. These answers you just write reverse answers here. And you just multiply, if you want accuracy, here multiply below that root, you multiply with 1.01 to get the accuracy. To get the accurate value, you just multiply with that quantity. So most of the times they ask you approximate only, by chance if they ask you, you just multiply with 1.01, which is telling about 10% accuracy more. So finally you will get close to 100% accuracy. Sneha Kumari, FL n of in brackets n is different, FL power n is different. Okay, FL of in brackets n will teach about only one frequency. FL by root over 2 power 1 by n minus 1 is only one frequency it is. But here we got net of n frequencies. Because of net of n frequencies, we are not writing in brackets n, we are writing power n. Because of n result, we are taking power. That is the indications we are taking. This is a different indication. Because of n result, we are taking like that. There is only one frequency we got. We take it as FL brackets of n. So like that we practice this content. Okay, these are indications because दोनों को same letter you cannot do. So that you will get confused for what that we have taken, for what this you have taken. There is a different situation, there is a different situation. Okay. So this is the story of these two formulas. So this is one important formula. So these two formulas will play a role to solve these questions. So I think finally, it is not two formulas in bandwidth, we have 4 different formulas. 2 formulas are related to a single identical techniques. If it is a non-identical techniques, the style of writing the answers are different. Because here we got the more number of lower cutoff frequencies, more number of higher cutoff frequencies. So resultant we are finding like this. Yes, Sabnidas, what you said is correct. FL in brackets of n, anybody say the word, it's a particularly for one frequency if you have identical, then you can do that. If you have n number of frequencies like this, you have to take power indication. Okay? Net power se practice karna. In denominator we have to multiply 1.01. Yeah, sorry, I think, Sahu, sorry. I think here it is not 1.01 by mistake I have written. Correct. 10% means it is 1.1 here. Total correct kar dijiye. It is 1. Sorry. So you said 10%. 1.01 means only 1% it will become. So by mistake I have written 1.1 you can take. Sahu has given that 10% meaning. Correct. It is not 1.01 here, it's a 1.1 because 10% you are asking. So please correct it. You write as 1.1 in place of 1.01. 1.01 is only 1%. it is, but is expecting 10%. So this completes the story of the concept. So finally, after getting this complete knowledge, let us understand what is the conclusion you can do for bandwidth. Here also, you are seeing bandwidth is decreasing. Here also, the bandwidth, if you see, the bandwidth we got for the cascade system. If you see the cascading system, here also we got the same thing. The bandwidth of cascade, here, the definition became as FH of power n minus FL of power n. This is the cascading bandwidth form. So here also, I think the bandwidth is coming less only here. Divyanshu, okay. Actually, from 4 days onwards, I'm very busy in work. That's why I'm not open the WhatsApp mobile, because I have two mobiles. One mobile will be always with me, another mobile will be somewhere in the bag. Okay, I'm not open from 4-5 days onwards. Today, definitely I'll open it and I'll add for you. Don't worry. Okay, because of hectic work I'm having, personal work also. That's the reason I'm not opened it. Today, compulsory has been added from October 1st onwards. You have been sending the message. Sorry for that. Today I'll add compulsory. Okay, and then today I'll make you to add. Divyanshi, today I'll add. Don't worry. Because I'm having morning to evening class. After that, traveling it is taking 1 and a half hour to go to home. After that, some work with personal work is going on. So I'm full busy actually. Up to 11 o'clock, I'm busy morning to 11 o'clock. Okay, my day is starting at 5:30 morning. 11 o'clock, I'm very busy. That is the main reason I'm not open the mobile. So today I'll open it and I'll just start for it. In previous case, A is multiplied by 2 times. Yeah, A is multiplied by 2 times. So write down a small conclusion here. A small conclusion. You can write here only. About bandwidth, if you want a conclusion, you can write a small conclusion here. Just write one conclusion. The multi-stage bandwidth is always less than single stage bandwidth. This is a very important statement again. After seeing these 4 derivations, 4 formulas, I got this meaning that a multi-stage bandwidth will be always less than a single stage bandwidth. This is the rule they kept. Multi-stage bandwidth will be always less than a single stage bandwidth. This is the second golden statement we got in integrated electronics. Okay. So these two things are very clear to understand. It's not created any trouble for you. So whenever the person said the gain is increasing in multi-stage, he has to lose the bandwidth that I want to tell in the class. So if you want to have a good research and gain, you want to increase it in the design of IC techniques, the bandwidth automatically you lose in the electronics. With this resultant formulas, you can understand it. So it is now 10:05. Let us start to take a break. So next, it is a part 1. Next part 1 more video will make to complete the remaining question concepts. Now at least we have covered 3 topics now. Remaining 3 topics are remaining now. One is the right stem concept. First I'll explain when I come after the break. After right stem, we have the 2 more topics. That is called cascode IC and dot pair. By 1 o'clock, we'll reach all these points. So now it is exactly 10:05, my friends. 25 minutes you can take break. 10:30 shortly we are going to start the class. Okay? I'm giving a break up to 10:30.